Okay, in this video we're going to talk about isomorphisms, and you should think that two spaces are isomorphic if they're essentially identical. So let me just write that down. Isomorphic vector spaces I'll just say this in quotes, essentially identical. Okay. In fact, isomorphism is a very important concept in mathematics. You have other types of isomorphisms. In general, isomorphism, iso means same, morph means form. So an isomorphism is a mapping that preserves the structure. So if you're talking about isomorphisms of vector spaces, you're talking about a mapping between two vector spaces that preserves the vector space structure. Now that's a little bit vague, but we'll see how that works out in the subsequent examples. So just keep that in mind. Isomorphism is a map that preserves vector space structure. The definition of isomorphism. So let's start out with some examples. Now we've seen several vector spaces that seem to be virtually identical. For instance, R2 and P1. P1 is the polynomials of degree 1. And you can see really that the behavior is just the same. 1, 2, this is an element of R2. And really this behaves just like 1 plus 2x. If you've worked with 1, 2 and 1 plus 2x, you see they really behave pretty much the same way. And here's another example. Minus 3 1/2 is just like minus 3 minus 1/2 x. You add vectors here the same way you add polynomials here. You multiply vectors here the same way you multiply polynomials here, and so on. So what makes the spaces alike, not just the sets, is that the association persists through the operations. So what does that mean? Take an equation like this in R2. 1, 2 plus minus 3 1/2 is equal to minus 2 5/2. I can write this equation in R2. I can write a similar equation in P1 that has the same structure and reaches the same conclusion. Remember that 1, 2 is pretty much like 1 plus 2x. Minus 3 1/2 is pretty much like minus 3 plus 1/2 x. And minus 2 5/2 is pretty much like minus 2 plus 5/2 x. So if I take this vector here, 1 plus 2x, that corresponds to 1, 2, and this vector here, minus 3 plus 1/2 x, that corresponds to minus 3 1/2, and I add them together, I'll get the vector that corresponds to the sum of the two original vectors. Similarly, if I have a vector in R2, 1, 2, and I multiply it by a scalar multiple, 3, I obtain 3, 6. Now, 1, 2 is associated with 1 plus 2x. That has a natural identification. And if over here in P1, I perform the same scalar multiplication, 3 times 1 plus 2x, that gives me 3 plus 6x, which corresponds exactly to the scalar multiplication in R2. So you can say this in brief, that operations in R2 correspond to operations in P1. Okay, and by operations, I mean either addition or scalar multiplication. So that's what we're seeing here, that this identification, which we can also call a mapping, this identification between R2 and P1 preserves the operation. Any operation in R2 has a corresponding operation in P1 that gives the same result. Okay. So more formally, we can think of each vector in R2 corresponding to a linear polynomial, and this defines a mapping. The vector in R2, AB, corresponds to A plus BX, which is a polynomial in P1. All right, this association holds through the vector space operations of addition. So as we've seen, if I add two vectors in R2, I get a vector in R2. If I add the corresponding polynomials, I get the corresponding polynomial. And scalar multiplication, if I multiply a vector in R2 by a scalar multiple, I'll get the result here in R2. I can perform the same operation in P1 on the corresponding vector, a plus bx, and I'll get a result that in fact is the corresponding vector to the result in R2. Now think about this. This is not something that immediately happens. This happens because these two vector spaces really can be closely identified. And in some sense, addition in R2 is the same, in quotations, as addition in P1. So this association or mapping preserves the structure of the spaces. And at the risk of repeating myself, in vector spaces, the structure that we're interested in is the additive structure, addition of matrices, and multiplicative structure, multiplication of vectors. I'm sorry, I said matrices, I meant vectors. Addition of vectors and multiplication of vectors. This structure of addition and structure of multiplication is preserved by the mapping or association between R2 and P1. Another example, think of 2 by 2 matrices. I can associate this 2 by 2 matrix with a vector in R4. So in general, what this means is if I have a 2 by 2 matrix, I take the 1, 1 entry and put it in the first entry of my vector in R4. I take the 1, 2 entry, put that in my second entry. I take the 2, 1 entry, make that the third entry, and take the 2, 2 entry, make that the fourth entry. So this is an association or mapping or function. All of those terms are synonymous. And it gives me a correspondence. Well, there's another synonymous term, correspondence. It gives me a correspondence between M2 by 2 and R4. Here's one particular example of that correspondence. As we said, the 1, 1 entry is first, the 1, 2 entry is second, 2, 1 entry is third, 2, 2 entry is fourth. And clearly I can do this with any 2 by 2 matrix. I can associate a 4-dimensional vector in this way. This association also persists under addition. We'll make the same check. If I perform this addition in M2, and I get a result in M2, I can translate this first matrix into R4. I can translate this second matrix into R4. I perform this addition in R4. I get a result in R4, and this result in R4 turns out to be exactly the vector that is associated with this result in M2. Okay, so the addition in M2 has a parallel addition in R4. You can almost think of these as parallel universes where everything that happens in M2 has a corresponding occurrence in R4. Okay. So here's another particular example. If I take this particular matrix in M2, this particular matrix in M2, I get this particular result, as you can verify. For instance, -2 plus -3 equals -5. And I can translate this sentence, this mathematical sentence, into a mathematical sentence in R2. 1 minus 1, 2 minus 2 is associated with this vector in R4. 0, 4, 3 minus 3 is associated with this vector in R4. If I add these two vectors, I get this vector, and this vector turns out to be exactly the vector that is associated with this result in M2. Okay. We can do the same thing with scalar multiplication. Here's the general statement, and here's a particular example. Okay. Multiply this matrix, 2 by 2 matrix, by R. I get the following 2 by 2 matrix. On the other hand, take this original matrix, find the corresponding vector in R4, multiply that by a scalar, obtain a vector, and this vector happens to be exactly the vector that is associated with this 2 by 2 matrix here. And here's a particular example that you can look at and verify that it works in this case. And any other cases work exactly the same way. Okay, so let's get down to the formal definition of isomorphism. An isomorphism between two vector spaces V and W is a map. We've been calling it an association or correspondence or a function. Those are all the same thing. It's just something that associates with every element in V, an element of W. Now, this isomorphism has the following properties. F is 1 to 1 and onto. You may have heard the word bijection. This is actually a bijection. Whoops, got some funny business here. Okay, so an isomorphism is a bijection, 1 to 1 and onto. It also preserves structure. If I have two vectors in the domain vector space V, and I take the mapping of the sum of these two vectors, that becomes the sum of the mapped vectors. So you can say that in shorthand, that the mapping of the sum is the sum of the mapped vectors. Similarly, the mapping of the scalar multiple is the scalar multiple of the mapped vector. Okay, and we say that these two vector spaces V and W are isomorphic. V is isomorphic to W. Okay, actually we will show shortly that if V is isomorphic to W, then W is also isomorphic to V. So really there's an equivalence relation that's reflected in this terminology. At this point, we've only shown a one-way definition that there's an isomorphism from V to W, but shortly we'll show that if there's an isomorphism from V to W, there's also an isomorphism from W to V. And that shouldn't be too surprising because here we have that this correspondence is a bijection. So it really goes both ways. All right, so here we have another example of an isomorphism that's up not one notch from the previous example. If we take quadratic polynomials, P2, this is isomorphic to R3. And this isomorphism really works exactly the same way as the isomorphism between R2 and P1. Now, when we were doing the isomorphism between R2 and P1, we were taking a map from R2 to P1. In this case, we're taking a map from P2 to R3. Now, you can pretty much see that we could have defined instead a map from R3 to P2. For instance, I could say G of A0, A1, A2 is equal to A0 plus A1x plus A2x squared. In fact, this mapping G is the inverse of F, and G is an isomorphism in its own right. So these two isomorphisms are inverses of each other. But the upshot is that P2 is isomorphic to R3, and what I've shown over here indicates that R3 is similarly isomorphic to P2. Okay, let's go ahead and verify that this mapping F is a correspondence, that is, that it is a bijection. And number two, that F preserves structure. And we have that equation with addition and scalar multiplication, that we need to verify both of those. Okay. All right, the first part of proving that F is a bijection is we have to prove that F is 1-to-1. We usually verify this property by assuming that the function yields the same output on two different inputs, and then show that the two inputs must be equal. That's a standard way of showing that a function is 1-to-1. So let's suppose that f of a0 plus a1x plus a2x squared is equal to f of b0 plus b1x plus b2x squared. Now the definition of f says that this polynomial is associated with this vector. Similarly, the definition of f shows that this polynomial is associated with this vector. Now, these two vectors are equal only if the corresponding entries are equal. A0 equals B0, A1 equals B1, and A2 equals B2. If those three coefficients are all equal, that means that the original polynomials must also be equal. Okay, so we've shown that if we start with any two inputs and their outputs agree, then the inputs must also agree. Okay, so that's the 1-to-1 part of this statement. Okay, the next part of the proof is that the function is onto. Now at this point, let me go over to a little picture that I've drawn to try to make this clear. We've just shown 1-to-1, and 1-to-1 says that if I take any element in W, which we're calling the codomain, supposing there are two different vectors that map to this element of the codomain, they must in fact be equal. So in fact, W has at most one pre-image. By pre-image, I mean a vector that maps to W. All right, so this picture here is 1-to-1, and we've shown this is true. Now we're about to show onto. Onto, the case is a little bit different. We take any vector W in the codomain W, and what we want to do is show that there exists at least one element in the domain that maps to that element W in the codomain. Okay, so 1-to-1 shows at most one pre-image. Onto shows at least one pre-image. If you have 1-to-1 and onto, that means every element of the codomain has exactly one pre-image. Now, since f is a function, we also know that every element in the domain has exactly one image. So this creates a 1-to-1 correspondence between the elements of the domain and the elements of the codomain. So I just give this picture to put 1-to-1 onto and bijection into perspective. Right. We finished with a proof of 1-to-1. Let's continue with the proof of onto. Okay. All right, now to show that f is onto, we usually verify ontoness by considering an element of the codomain. All right, now he chose V here. I think that's a little bit unfortunate because we've been using W for the codomain. So I'm going to choose an element W in the codomain. Now in this case, the codomain is R3 because we're mapping from the polynomials P2 to the vectors R3. Okay. Now remember that when we want to show onto, we're trying to show that there's at least one vector that maps to this element of the codomain. And there is. If I take the polynomial, I'll write it again, w0 plus w1x plus w2x squared, this element of the domain will map to this w in the codomain. That establishes that f is onto. Okay, so we've shown that the mapping f is one-to-one and onto. We want to show condition 2, which is that the function preserves operations. Okay. Now there are two operations, so this proof has two parts. First, we need to show that f preserves addition. Okay. So consider f acting on the sum of two elements of the domain. Okay. So we have the function f acting on the sum of two elements of the domain. Here's one element, a0 plus a1x plus a2x squared. Here's the second element, b0 plus b1x plus b2x squared. Okay. Now, in order to evaluate f, we can do the usual algebraic manipulations and create a single polynomial. a0 plus b0 is the constant term of this combined polynomial. a1 plus b1 is the x term. a2 plus b2x squared is the x squared term. We've just done some rearrangement and distribution. Now, according to the definition of f of this polynomial is going to be constant term, x term, and x squared term. I should say, rather, constant coefficient, x squared coefficient. Those are the entries of the vector in R3 that consists of f of this polynomial. Okay. But notice that this vector here, just by using ordinary vector addition, I can break it apart into two parts. The part with the a's and the part with the b's. Okay. And this part here with the a's is simply f of the polynomial with coefficients a0, a1, a2. And this part with the b's is simply f of the polynomial with coefficients b0, b1, and b2. Okay. So what we have altogether, if you go from first to last, you have f of a linear combination of polynomials. I'm sorry, f of the sum of two polynomials is the sum of f of the individual polynomials. Okay. Finally, we need to show that f preserves scalar multiplication. The proof is very similar. Take r times f of an arbitrary polynomial, but f of this polynomial is a0, a1, a2. If I apply r to that, I get ra0, ra1, ra2. But by inspection, this vector is exactly f of the polynomial with coefficients ra0, ra1, ra2. So if you take the first and last statements of this sequence of inequalities, you get exactly what you want. That the function f preserves scalar multiplication. I can take f first, then multiply by r. That's the same thing as multiplying by r first and taking f. Okay. So in summary, we've proven all the properties of isomorphism. We've shown one-to-one onto, preserves addition, and preserves scalar multiplication. So that gives us, in the end, that this function f is an isomorphism. Okay, I'm going to pause here.